Welcome everyone. Welcome Julio again, and let's start with the first session in the morning.
Okay. Hi everyone. Welcome back. Okay, let's start just with a. Can you hear me well? Yeah. Okay. Let's start with a little recap of what I explained yesterday. So we are on. I motivated why we are interested in the S matrix or scattering amplitudes because we want to understand time evolution of certain processes in gravity in particular. And I told you that something nice is that these objects are highly constrained by various basic principles. So we discussed that the idea of symmetry, Poincare symmetry in particular, tells us that amplitudes tell us about the scattering of particles that are labeled by some momentum that will square to the mass of the particle and carry some representation, irreducible representation of the little group. And we discussed this both for massive and massless particles. Then I explained that locality and unitarity dictates which singularities the amplitude can have. So for instance, it tells us that when some momentum, say now we talk about massless particles for simplicity, if we have some sum over momenta, capital P, that goes to 0, then there can be maybe a pole, maybe some logarithms, but in particular if there is a pole, then unitarity tells us that the residue of that pole will factorize into like some simpler processes. So we were drawing these pictures with these blobs where this was, say, a 4-point amplitude. And then if I take the sum over here, this is P1 plus P2 squared to 0, then this will factorize into two different processes, and the divergence you can think of as the very long time that happens between these processes. And I didn't have time to explain causality. I decided to just make a quick comment about it because I want to cover more ground. But the basic implication for causality is that, in fact, this amplitude not only makes sense for real and physical values of the momenta, but we can give kind of imaginary parts to the momenta and extend this amplitude to some complex analytic function, like elsewhere in the complex plane. Exactly in which regions depends on the details. But the first approximation, just think that the amplitude is some complex function of the momenta. And it also tells you that you can relate incoming and outgoing states. So from now on, for simplicity, I'll just think about amplitudes with all momenta outgoing. And if this is confusing, just think that you can analytically continue the energies so that some of them are actually incoming particles. Okay. The goal today is to use this to actually compute some amplitude. So we're not going to write a Lagrangian. We're just going to apply these principles and build some simple gravitational amplitudes. Okay. Any questions about this before I start? Okay. So the key tool that we will use is to make a smart choice of variables to be able to construct this. And we'll still be guided by symmetry. So I'll introduce something called spinor helicity variables. So this is now going to be specific to d equals 4. Okay. And we want to have variables that nicely manifest kind of both the little group properties, but also kind of the Lorentz symmetry or Poincare symmetry of the amplitude. And we're going to use this well-known fact that if you have SO1, 3, this is basically isomorphic as a Lie algebra to a pair of SU2s. You can think of one of these as acting on left-handed spinors, one of these acting on right-handed spinors. Okay. So we'll have indices alpha carried by left-handed spinors that will transform under some matrix belong to this SU2 left, which is part of this of the Lorentz group. And we will raise and lower indices with an invariant of this group. Okay, so now I'm going to introduce little technical machinery. So we'll define anything with some index raised with this epsilon, two-dimensional epsilon tensor, where this dot 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 can be any other indices that, that I have. Okay, and similarly, we'll have indices, dotted indices, which will be right-handed spinors, which will transform under matrices that belong to the other SU2. And also we'll raise indices with also the corresponding invariant antisymmetric tensor. Okay, so this is just the usual 0, 1, minus 1, 0 matrix. Okay, so what's the trick that we're going to play? So amplitudes are a function of momenta and of these kind of little group representations, and we want to make this as manifest as possible. So let me do the following. So for now, let me focus on massless particles, and I'll comment on massive particles in a bit. So I'll construct the following object. So I will just contract any one momentum with this matrix, which is just a matrix that the zeroth component is the identity, and the x, y, z components are the usual Pauli matrices. Okay, so what is this object? This object will be something like P0 plus P3, P1 minus I, P2, P1 plus I, sorry. Okay, so this is a very simple 2x2 matrix, which we constructed using a 4 momentum. And then why is this nice? Because now this has these indices, so a Lorentz transformation on this P. So if I have transformation P, say mu, goes to lambda, mu, nu, P, nu, this can be equivalently done by taking this P alpha alpha dot and transforming it with these kind of matrices that I wrote here. Okay, so these are 2x2 matrices, and this is just the realization of this fact here. Okay, that I can just think of 4 vectors here, they transform under kind of a bispinor representation in this SU2 language. Okay, and generally the statement is that the determinant of this matrix, P alpha alpha dot, will be equal to the mass squared, which in this case, for now, we will choose this to be 0. Actually, let me comment on both massless and massive for now. Then we'll switch to massless. Okay, so we have some matrix whose determinant is given by the mass, and we know how it transforms under these Lorentz transformations. But we can do even better. So we can introduce now some nice variables, depending on whether we have massive or massless particles. Okay, so let me first comment on when you have m equals 0, then what's special about this matrix, this 2x2 matrix? The determinant is 0. What does this mean? It has a 0 eigenvalue, so it has reduced rank. And in particular, that means that I can write it as a product of 2 vectors. So I can just write it as some lambda tilde, each one with one of these indices. Okay, so this is nice. And then if the mass is not 0, then it doesn't have reduced rank. But I can always write it, because it's a 2x2 matrix, I can write it as a linear combination of a pair of pairs of vectors. So I can write P alpha alpha dot as something like this, epsilon ij, lambda I alpha, lambda j alpha dot. Okay, where these ij's are just kind of 1 or 2. Okay, and so this is just saying that I have this being something like lambda 1, lambda 2 tilde, minus lambda 2, lambda 1 tilde, which is just some parameterization in terms of a pair of these vectors. Okay, but I'm going to argue now that this decomposition is very useful to understand the little group, and that these variables are the right ones that will let us understand these representations of the little group. Yes? So if they just have one index, they're just vectors. So they just have 2 components. So this here is a 2x2 vector. So if you want, you can think of this as the tensor product of these 2 vectors will give me that matrix if it has a reduced rank. Okay, if you wish, it's just a spectral decomposition. I can write any matrix as basically its eigenvalues and a projector in each eigenvalue, but this one, because it has a 0 eigenvalue, then I just need a single pair of 2x2 vectors to write it in general. Does that make sense? Okay, so why are these variables useful? So remember the m equals 0 little group was just U1. Okay, it was ISO 2 or something like that, but we argued that the representations that we care about, they're just representations of U1. And remember, the little group is just the group of transformations that leave the momentum invariant. Okay, so then looking at this formula, can someone come up with some transformation that leaves this momentum invariant of these lambdas and lambda tildes? Okay, is there some ambiguity in the definition that I wrote here? A phase, exactly. So I can transform lambda to t times lambda, where t was this kind of phase belonging to U1 that I introduced yesterday. And if at the same time I take this lambda tilde and scale it with the opposite power, that leaves this momentum invariant, okay? Because I'm just multiplying this by inverse values. Okay? So this is very nice because it tells me that these objects naturally carry a nice representation of the massless little group. And because of this, amplitudes of massless particles will be naturally, instead of thinking about them as functions of momenta and this carrying this representation, I can just write it as a function of these variables, of these lambdas and lambda tildes. Okay, so the amplitude, if I have massless particles, it will be a function of this lambda 1 tilde, lambda n tilde. And because these ones naturally carry a representation of the little group, then this is kind of the nice set of variables that we can write scattering amplitudes are. And even more, there are such functions, but we described exactly how states transform under the little group. So remember that I told you that if I act with a little group transformation on a massless state, so if I have this kind of P with some representation, and this has m equals 0, so little group transformation just gives me t to the minus, so I guess the representation will just be the helicity label. T just gives me this phase with some power that depends on the helicity times the same state. That means that amplitudes are such functions that they have specified homogeneity in each one of these guys, okay? Because they have to transform under the little group, because they're just overlaps of states. And we know precisely how these variables transform. So the idea is that these amplitudes have specified homogeneity. So if I rescale kind of each one of these variables with a corresponding t, then this will be just product. So let me also write an I here. So this will be a product over I of ti to the minus 2hi times the amplitude, which depends on the same things. Okay, so amplitudes are just homogeneous functions of these spin or helicity variables. Because the amplitude is an overlap between particle states, and particle states carry a representation of the little group. Okay, so that's the comment I made yesterday, that usually because we think that amplitudes are a function of Lorentz products, that they're Lorentz invariant, but the catch is that actually polarization vectors, they're not Lorentz vectors. Polarization vectors, they're Lorentz vectors, which in addition carry a representation of the little group, which is why also typically amplitudes are functions with specified homogeneity in polarizations. Okay, in the problem set, you will play this kind of a game with polarizations instead of with this spin or helicity, because you can also play this bootstrappy game of which we're going to play, of trying to fix the amplitude based on these kind of properties. But notice that so far there's no notion of gauge anything, even though for writing like gravitons or photons, I would need to introduce some gauge symmetry. Here, there's no polarization, so there's no gauge transformations, there's nothing like that. I'm just saying that the amplitude is a function of these variables with certain homogeneity. Yes?
Right there, for example, instead of that t, you use, for example, t equal 3. It also works?
It also works, yes, that's right, yeah. So it doesn't matter that much that this is a phase, but turns out that, yeah, the other, if this is a complex number not equal to 0, it also works, but only the U1 tells us about the little group, so usually we just think about that, yeah. Okay, very quickly, what about the massive case? Even though we will focus mostly on massless particles. So the massive little group, we said it was SO3 or SU2. Okay. So now we think which set of Lorentz transformations live this invariant. Okay. So let me just consider some Lorentz transformation on these lambda spinners, which now carry this index. And in general, this will give me some linear combination, because now I have a pair of this. So this is a 2x2 vector or spinner. So this pair just spans the full space of these guys, right? So I can write this always as Lij times the same thing. And similarly, I can write some other kind of Lij lambda tilde. And for this to live invariant, this momentum, what I need is that when those matrices are contracted with this epsilon ij, they leave them invariant. Okay, so basically I need that L, let me just write it explicitly. And what does this mean? This just means that these L's belong to SU2. So we actually recognize these indices also as little group indices. So these IJ, actually, they're SU2 indices also, but now of the little group. Not to be confused with the actual group of Lorentz transformations that acts on these guys, okay? So this is just a subset of Lorentz transformations that leaves the momentum invariant. Okay, and same thing as I said for massless. Let me not write it because we won't use it in this lecture. But we know how states transform under this SU2 little group. Remember that states were symmetric traceless tensors of these I, J, K indices that I mentioned yesterday, which are precisely these indices. So once again, amplitudes of massive particles will be functions of these lambdas, which have the right number of these indices. Okay, so they just carry the right number of symmetric traceless SU2 little group indices. Okay, so let me just write it in words. So massive amplitudes have specified rep of SU2 little group. So what does that mean? This just means that there will be functions of these lambda I, lambda tilde I. We just have the right number of indices. So for instance, they will have like I1, kind of I2S1, if S1 is the spin of the first particle, and then kind of I prime 2, S2, et cetera, okay? So they will just be a function of these things that has the right number of indices instead of having the right homogeneity, okay? But they're still a function of these spinoholistic variables and which always keep track of this little group representation. Okay, so you might say, why do I care about this? So let's now try to understand what other restrictions there are on this function. Okay, so now I just translated what I said yesterday. Amplitudes are a function of momenta with little group. Now I said it's nicer to write it in terms of these variables. Now let's think about the symmetry, because we still haven't imposed all of our symmetry. Right, so what do the symmetry generators look like here? So for instance, the momentum generator, this just looks like sum over lambda I, lambda tilde I, over all particles. Okay. The angular momentum generator that generates the SU2 left, so that acts on the left-handed spinners, will be something simple like lambda alpha dd lambda beta plus lambda beta dd lambda alpha. And there will be kind of a corresponding J tilde, which you can find, but it's basically the same thing with lambdas going to lambda tildes. And there's two extra that could be useful. There's two other things that I can write. So I can also write a helicity operator that acts on each particle, just as the thing that counts the homogeneity in the spinners, right? So I'm just going to write lambda dd lambda alpha plus lambda tilde alpha dot d lambda tilde alpha dot. Okay, so this is just counts how many powers of lambda I have minus how many powers of lambda tilde I have for each particle. So if I act on the amplitude with this is just going to give me minus 2 hi times the amplitude, which is the fact I mentioned before that they have specified homogeneity, right? Then how do we impose momentum conservation? Momentum conservation means that when this thing acts on the amplitude, I should get 0. So I want to impose, this is 0, but this is just multiplicative. So what is the only way that I can satisfy this equation if this is just a number that I'm multiplying the amplitude by? So this implies that the amplitude needs to be proportional to a delta function of momenta, right? So it just tells me that momentum is conserved. And now what about this one? So if I act with the generators of angular momentum, or these left or right-handed Lorentz transformations on the amplitude, I also want this to be 0, because I want it to be a symmetry of my amplitude, full Lorentz symmetry. Okay, so, but okay, this is now a non-trivial constraint, because this is a differential constraint in the amplitude. Okay, so, but this just means that I need to build SU2 invariants. Okay, because this is just generates these SU2 left rotations. So as long as I write something where all the alpha and indices are absorbed, then this will be invariant. So this tells me the following. So let me introduce the following combination. I'll denote by these angle brackets ij, just as a contraction using this epsilon, this two-dimensional epsilon symbol of lambda I alpha, lambda j beta. So this is an invariant. You can check easily that this generator, so this is sum over all particles. Sorry, forgot about that. You can check that this thing is precisely annihilated by this, just because it doesn't have any indices. Okay, so it's just a rotational invariant. So that means that the amplitude, in order to satisfy this, the amplitude actually will be a function of these ij's. And similarly, if you impose that j tilde is 0, it tells me that the dependence on the lambdas and lambda tildes can only come through the corresponding bracket. So there's also this angle bracket ij. So what is this angle bracket? Here, let me just write it here so that you remember. So ij is epsilon beta, and square bracket ij is just the corresponding thing with okay, so you can just check that using the chain rule that if we write the amplitude as a function of these brackets, then it will satisfy all of these constraints. Yes. Yes, so these are all contracted. So this just has a particle index. So this I is just an index telling me which particle. No, this is just a badly erased, yeah. So I just have lambda I alpha, lambda tilde I alpha dot, lambda tilde I alpha dot. Okay, so all of the alphas and alpha dot indices are contracted. So this is just counting the homogeneity. So this is the same statement as before, that they have to be homogeneous functions. That's right, yeah.
Sorry, at the risk of exposing myself, I kind of
So
So, since we're working with spinors, there are left and right indices, alpha and alpha dot.
yes.
That I got. But where do the lambda and the momentum and angular momentum can be constructed such that why are we finding these operators in exactly, and why do they? How can I see that these can be expressed in terms of lambda?
So you can do it, for instance, by doing the change of variables. So you could express all of these things in terms of momenta,
Okay.
and then just doing a change of variables to this lab. I told you how to translate any momentum. Remember that we wrote that
Yes.
there was like P alpha, alpha dot? Yeah, right. So if you just do that change of variables, then it's just a change of variables. Yeah.
After you said that for masses you had a determinant equal to 0, it's not related to that, right? You can do these change of variables both to massive and massless.
So massive, there's a pair of spinors per particle, as I explained, with these capital IJ indices. All of these I wrote now for massless because it's simpler. So you can try to do the same as an exercise for massive. It's not very hard. So all of this now is for massless. So this is M equals 0 kind of Lorentz or Poincaré generators. And the point of this, so the question that you're asking, what is the point of this, is that we want to impose all of the symmetry on the amplitude. So first I just told you that it's a function of momenta and some representation of the little group. So we identified that these lambda tilde variables are kind of the nice variables that we can choose that let us make this manifest. Of course, the amplitude still needs to be invariant. Yes.
That's what gives us the condition for the amplitude.
That's right. Yeah. Yeah. So that's why this is momentum conservation. So kind of the momentum operator needs to annihilate the amplitude, which tells us that the amplitude conserves momentum. These are the generators of Lorentz transformations, so the SU2 left, SU2 right, which need to annihilate the amplitude, and that tells us that it's actually not only a function of these lambdas and lambda tildes, but in these particular combinations, which are these angles and square brackets. Okay, and in a second, what we're going to do is just start constructing amplitudes directly in terms of these variables and impose all of these conditions, and we will see how they're super constraining. We'll just be able to write out the answer without any work. Yeah, so bear with me because, okay, we are building up the machinery, but we're almost there. Yes? Yes, that's right. Lambda are, say that again? They're commuting variables, yes. They're just numbers. So they're spinors because we just want them to carry some representation, but they're not actual, they're not spinors as the spinors in a Lagrangian that have to be Grassmann or, yeah, they're just numbers. It's a convenient parameterization of momenta and polarization. We'll see later on how polarization arises, but the polarization is a weird object. We'll see when we try to write in terms of these variables that it involves some arbitrary choices that have to do with gauge invariance and all of that. But yes, that's right. This is antisymmetric. So II or JJ is 0. Okay, so yes. In the particular, it's Poincaré covariant, but in this particular sense that I described, that there's this helicity transformation, which does transform the amplitude. So this carries some quantum number under this operator, but it's invariant under these rotations. Okay, so this is the generator of the little group. These are just the usual rotations that act on the momenta. So for instance, these operators act on this alpha alpha dot, so they're not part of the little group. So we've kind of, using these variables, we've cleanly separated the part that actually transforms the amplitude from the transformations that don't. Yeah. Okay, more questions. Keep them coming. Yes? Yes. So for massive particle, so let me just list the indices that we have. So for massive particle, we have these indices, which is just the particle index, which just tells me if I have particle 1, particle 2, particle 3 in my process. I have the alphas, which are like SU2 left indices, just Lorentz indices. I have alpha dot, which is SU2 right. And then I have these I or J, these capital indices, which are SU2 little group indices, okay? And the amplitude only carries these ones. Because again, if you run the same argument, I didn't write the Lorentz generators in the massive case, but you can already see that if I want, there will be an expression analogous to this. So if I want to build amplitudes which are invariant under these generators, I will have to soak up all of the alphas and alpha dot indices, and I can still construct these brackets, except that now they will carry little group indices. Okay, so for the massive case, what will happen is that amplitude will still be a function of these brackets, but now I have a pair of spinors per each particle, so they will have an extra little group index. So I will have things like I, and like, for instance, you could have I1, I2, if it's a spin 1 particle, sorry, no, so this is always I1, and then J, I2, right? And for instance, if you had a spin 1 particle, so if particle 1 is spin 1, then this amplitude will have like I1, I2, because it has to have 2s indices and other indices for the other particle. Okay, so it will have to be a function of these brackets that has the right number of indices, and they will be symmetric and traceless. Yeah. So that's more complicated, so we won't play so much with that. We'll just construct one example of a massive amplitude later. But okay, this is all a bit boring. It's just introduce a bunch of things. So let's see the power of this. So now we're going to construct finally some amplitudes. So we've reached a place where we can finally calculate something. Yes? No, these are Lorentz indices, not little group indices. Yeah. Yeah. So remember that we are using the decomposition. Okay, so let's just write 3-point amplitudes. And to show you how powerful it is, we're actually going to construct the 3-point amplitudes. At the end of this, you will see that it's very easy to construct the 3-point amplitudes for any spins, any helicities. Okay, so we're going to do massless 3-point amplitudes. You'll see that the same procedure I'm going to carry out now will fix the amplitudes for any. So I'm going to have this kind of blob where I'll have like particle 1 with helicity 1, particle 2 with helicity 2, particle 3 with helicity 3. And in one fell swoop, we can construct all of these 3-point amplitudes very easily. Okay, so what's the magic here? So let's think back to those constraints. So something I need to satisfy here. The first thing is momentum conservation. Right? So what is momentum conservation in this case? So I have to satisfy lambda 1 tilde, plus lambda 2 tilde, lambda 3 tilde equals 0. Okay, so I have this, okay, make all this P alpha alpha dot. So all of these have alpha alpha dot indices. Okay, so why is this, okay, this seems a triviality. It's some quadratic constraint, it's not a linear constraint, unless in momentum space. But this will imply that actually there's some special kinematics at 3 points, so that these spinors cannot be arbitrary. So to show this, let me contract this with alpha 1 upper. Okay, so let me do the following. So let me do alpha lambda 1 beta, and then this p alpha beta. So what this is going to be, this is going to be 1, 1 lambda 1 tilde, but this is 0, plus 1, 2 lambda 2 tilde, plus 1, 3 lambda 3 tilde equals 0. In particular, this tells me that lambda 2 is proportional to lambda 3 tilde. Okay, with a specified proportionality factor, which is given by this. Okay, so these are 2 by 2 vectors. So I have a linear relation now between them, and these things are just numbers. Okay. But I chose lambda 1, but I could have chosen lambda 2 or lambda 3. So it turns out that that we have a choice. Either, so there's 2 ways to satisfy this constraint. Either all of the lambdas are proportional to each other, which means that all these angle brackets will be 0. Okay, because if lambda 1 is alpha times some constant k times lambda 2, this is linear in the spinors, and it's antisymmetric. Okay, so this will always give me 0. Or the lambda tildes are proportional to each other. And then all the square brackets are 0. Here? Sorry, yes. Thanks. Yeah, and all of these have an alpha dot. Sorry, I'm being a bit lazy with the indices. But ask me if it's not clear.
Can you explain why you have 2 to index 1, H2, and 1 to index 1, H1?
So this is just P1 alpha alpha dot plus P2 alpha alpha dot plus P3 alpha alpha dot equals 0. And I just decompose each one of the momenta as the pair of spinors using
No, I picture the group.
this.
3H3.
These are just the labels. I'm just saying that I have particle 1 with helicity H1, particle 2 with helicity H2, particle 3 with helicity H3.
Okay.
Yeah.
Okay, thank you.
Okay. Note in particular, this means something else. So what is the quantity, like the usual Mandelstam invariants, which are kind of Pi plus Pj squared. If you write in terms of the spinors, this is something like 2 times P1 dot P2, because P squared, sorry, Pi dot Pj, because P squared are 0 for massless particles. And you can check, just using this translation, that this, in fact, will be equal to Ij. So at 3 points, all these kind of products of momenta, so Pi dot Pj, they're all 0. Okay, because either the square brackets or the angle brackets are 0. Okay, so this amplitude is going to be very simple because it cannot be a function of any product of momenta. It can only be a function of either these lambdas or these lambda tildes. Okay, so what this means that here we would have that the amplitude is just a function of these square brackets Ij, and in this case the amplitude is just going to be a function of these angle brackets. Okay. So we can just write an ansatz now, because we only have how many brackets? We just have 3, because we can have 1, 2, 1, 3, or 2, 3, because this thing is antisymmetric. Okay. So in this case, this will be some G tilde 1, 2, 2, 3, 3, 3, 1 to some power, A, B, C, which in principle could be negative, but just some power. In this case would be G, 1, 2, A, so let me put tildes here, 2, 3, oops. Okay, and we're almost done. Because, okay, now we just need to determine these powers here. But we haven't imposed all of the constraints. We just imposed momentum conservation and Lorentz symmetry. We haven't imposed yet the little group scaling. Okay, so what's the statement? So let's focus on this amplitude for simplicity. The statement is that if I take this amplitude, if I just rescale lambda by this t, so here we have T1, T2, and T3. Let me write it explicitly. T1, lambda 1, T2, lambda 2, T3, lambda 3. This has to be equal to T minus 2, H1, T2 minus 2, H2, T3 minus 2, H3. So this has specified homogeneity in these lambdas variables, but each one of these brackets also has specified homogeneity. Sorry, I can't. They're just powers. They're just some power to be determined. Yeah, but now we are just going to determine them by imposing this, right? So now we know that the amplitude has to have a specified homogeneity in these lambdas. Okay, so I'm just going to write some linear equations. Okay, so if I scale 1, then only the first and the third term depend on the spinor 1, right? So I will have A plus C equals minus 2 H1. 2, I have A plus B equals minus 2 H2, and B plus C equals minus 2 H3. Okay. So now you can go ahead and just solve. We have 3 equations for 3 unknowns. We have specified helicities. So we fully determine these powers using this basic principle. So we've constructed the amplitudes for any 3-point amplitude for massless particles with any helicity. Yes? Yeah. I did it as an example to show that if I multiply with lambda 1, that implies that lambda 2 is proportional to lambda 3. But then I said that this was no particular choice. I could have chosen lambda 2, which would have told me that lambda tilde 1 and lambda tilde 3 are proportional. Or if I did the other one, so that shows me that all of them have to be proportional. Yeah. Yeah. Okay, more questions? Yes. Yes. Yeah, here I wrote it in the usual Lorentz notation, but if you wish as an exercise, you can try to prove this. That if you just write the usual Lorentz product, so essentially the exercise tells you that if you have mu nu and you contract with 2 copies of these sigma matrices, then this will give you 1/2 of alpha and kind of alpha with the indices. See if I have like, so you can just try to show this. It's just a numerical identity. Yeah. But the important thing was that this is just a function of these brackets at the end of the day. It always is, but in particular here, it's even simpler because I cannot write any product of momentum. And by the way, in the problem set, you can think a bit harder about why this is the case. Yeah. Okay, so we are done. Let me write an example, since we care about gravity ultimately. So let me write now the 3 graviton amplitude with fixed helicities. Okay, so let me write the amplitude for 3 gravitons. So the first one has helicity -2, the second one has helicity -2, the third one has helicity +2. Okay, so that means there I would have 4, 4, and -4 in these equations on the right-hand side. So if you just solve them, it tells you that this has to be a constant, which I'll call kappa, and then 1, 2 to the 6, 1, 2 squared, 3, 1 squared. And there's actually another solution, it turns out. Oh, no, sorry, this is the only solution. And then you can see that this thing has dimensions of -1. Actually, you can check that this thing is 8 pi, square root of 8 pi g Newton, if you do the calculation from. Okay, in the problem set, you will also fix a constant like this in the dimensions by comparing to Newton's potential to realize that here I just wrote some constant, which I cannot determine by this argument, but the kinematic structure I have fully determined just by solving these linear relations. Okay, let me do another example. If now so this is just the Hilbert 3-point amplitude. Well, this is just because the amplitude in 4 dimensions needs to have dimension, let's see, I always forget. It's n minus 4, where n is the number of particles. Okay, and this is because it's something that you need to square and integrate over phase space to get a probability, so you can just, this is just dimensional analysis, that amplitudes always have this fixed dimension. So that's why I know that this has dimension -1, and this will be. No, these are 2 different amplitudes. Yes, yes. These will be 2 different amplitudes. So for instance, if now I switch the helicities to be plus, plus, minus, then you will see that you can only write that in terms of the other brackets. And there's actually no way to satisfy those equations with powers that make sense. Yeah. Why don't you cancel what? Oh, sorry. This is just a typo. 2, 3. Sorry. Yeah.
How can I figure out which one I have to use exactly? Which one of the 2?
You just try. You just try to satisfy those equations with the powers that you have here, and you'll see that only one of them actually will. Basically, you could do something like invert this. So if I just have 1 over this, that will flip off the helicities, but then you will find that this constant doesn't have a sensible scaling dimension. So you will see that this cannot correspond to anything like as sensible, yeah, just by dimensional analysis, yeah. So let me give you another example, which is now for 3 gravitons with the same helicity. So if I have, let me do it with plus now, 3 plus, right? Then this will be alpha, just 1, 2 squared, 2, 3 squared, 3, 4 squared. Okay, now the dimension of this thing is -5. So what does this correspond to? So if I have a coupling that has dimension -5, so this coupling here actually is going to be the coupling of R cubed. So some non-minimal interaction between gravitons. And you can just count also here derivatives. So maybe I'll mention in a second how these relate to. Yeah, so maybe I didn't mention this, but these brackets, for instance, this ij, you can think of them as the square root of this Sij, so of the product of the momenta times some phase, and then the lambda tildes is just a complex conjugate. Okay, so you see that each one of these guys goes like one derivative. So you could have also counted derivatives here and see that this interaction is a two-derivative interaction, but this one here is actually a six-derivative interaction, because I have 6 powers of this. Okay, so you see that I can not only construct the usual 3-graviton amplitude, but also with non-minimal couplings with very little effort, just by doing this counting. So now you can go ahead and you can take out your GR textbook, you can take your Einstein-Hilbert action, you can linearize around flat space, you can expand to the 3rd order in the perturbation, you can fix a gauge, you can do all the weak contractions to extract the 3-graviton vertex. If you look it up, it's like 10-page expression. But when you put it on shell, it just reduces to this. Okay, this very simple object that we can obtain directly using these ideas. Yes? By the fact that this has negative mass dimension coupling. These amplitudes, these 3-point amplitudes, yes, they're fully fixed by kinematics. They're complex also. So these actually, you see, like these things are complex conjugate to each other if you want that momentum to be real. So you can only satisfy these for complex momenta, right? That's why it was important that we think of the amplitudes as functions of complex momenta. So actually, you cannot access these 3-point amplitudes with real kinematics. So we never measure these 3-point amplitudes in an experiment. But we can use them now to build more complicated amplitudes. Okay, so as an exercise, you can try to build the 4-graviton, the 3-gluon amplitude, which, as you see, will just be the square root of this. But now we'll have to have some antisymmetric structure constant here for it to satisfy both symmetry. Okay, because the thing will be antisymmetric. Okay, let me do another example quickly. And we'll see that there's a little issue. Okay, so now I want to construct the 2-scalar 1-graviton amplitude, but where the scalar is not massless. Okay, so here, as I told you before, I have P1.P3 just by momentum conservation. This is going to be, okay, so the labels here will be 1 and 2 are the scalar, 3 is the graviton. Right, so P1.P3 actually by momentum conservation should be the same as P2 squared minus M squared. It's actually 0. You can just check by completing the square. So how do I write now something also satisfying? Now I want to write something that only has homogeneity in the graviton. But it's a bit hard because I want it to be completely like invariant under rescaling the lambdas of the scalar, okay, the momenta of the scalar. But I cannot write 3-3, for instance, because this would be antisymmetric. So I need to do something funny, okay? So okay, there's the following object. So if I contract with lambda alpha, this means that this needs to be proportional to lambda 3. Okay, because in this product, for this to be 0, the only way is that one satisfies this equation. Okay, think of this again as this being sort of like 1, 3, 3, 1, except that now 1 is massive. So what is this x? This x is something funny. This x is the following. It's P1 alpha alpha dot, then lambda 3 tilde alpha dot, and then some reference alpha. So this is some arbitrary reference spinner. And then, because I wanted to have the right homogeneity, so this now has to have So this was a tilde, this is untilde. So I need to divide by this. Okay, so this will transform exactly like the compensating factor between lambda 3 and lambda tilde 3. Okay, so if I rescale this with respect to lambda 3, it needs to scale like this. So it needs to cancel the scaling of lambda 3 and then transform like lambda 3 tilde. Okay, this is a very weird object. So what is this? Turns out that this is something simple. This x is just epsilon dot p, where epsilon is the polarization of the graviton. But as I told you, polarizations are weird objects because they transform under the little group and under Lorentz. They're only defined up to some gauge transformation. And indeed, you can check that if I change my choice of this reference spinner, because I can always choose a, say I chose some lambda prime, which is not the original one that I had chosen, what is it going to change by? So this quantity here, so let me write in this notation the following, which is lambda 3. I guess here I wrote the other one. So let me just leave it as an exercise. And the key is just to realize that any choice is always spanned by lambda itself and lambda 3, because I just need to choose a pair of spinners, right? So if I have some eta prime, this will be some alpha eta plus A eta plus B lambda 3. So exercise, check that if I go from the reference spinner to a different reference spinner, this just transforms by something which is proportional to the momentum. Okay, so we see that indeed when we try to write certain amplitudes, there's these weird reference spinners that appear, and that is giving us a clue that there's something like gauge invariance, something like that, which is kind of annoying. But we'll see that all of these reference spinners actually disappear when we look at higher point amplitudes. It's just that at 3 points, it's very hard to construct some invariant that has the right homogeneity properties. So only at 3 points we need to play this game. And then at higher points, all kind of trace of these reference spinners and polarization vectors will be completely gone. Okay, so this means that the amplitude that I wanted to write, where I have like the first two particles being scalars and the third one being a graviton, say with helicity +2, it's something very simple. I will call it kappa prime x squared. Because now this will have the right homogeneity properties because this scales in the right way. Okay, so x under the little group scales like t to the minus 2. Sorry, 2. Okay, so maybe this is a bit boring, but we still have 20 minutes, so let's also do 4-point amplitudes. And now we'll see some of the magic, continuing and using some other of these ideas, this idea of locality and unitarity also being useful. Okay, so for 4-point amplitudes, as usual, we use these variables, these S, T, and U, which now they can be non-zero because we don't have these special kinematics. And let me introduce a shorthand for this combination here. So this kind of combination where I have a momentum that is massive and it's contracted with two spinors. So let me just denote it by this. So I just have the angle bracket corresponding to this spinor, which is left-handed, the square bracket, and then in between, I just have some momentum, which is contracted between the two. Okay, so now we're going to play the same game. So now I want to construct the Compton amplitude. So I want to construct the amplitude of two scalars. So 1 and 4 are going to be scalars. And 2 and 3 are going to be gravitons with helicity -2 and +2. Okay, so now this is going to be more complicated because it can depend on S, T, and U. But again, the little group will be very constraining. So the little group tells me that this needs to transform with T to the 4th when I rescale this variable, and T to the -4 when I rescale these variables that correspond to 3. Okay, just again, the homogeneity in each one of these spinors. So one way to write this is if I just construct this combination. Okay, so now this, I have lambda is negative, so I have this angle bracket to the 4th power, so this will have the right homogeneity. This is just a momentum, right? So this has same number as alphas and alpha dots, so this doesn't transform in the little group. And then 3 is the angle spinor, the tilted spinor corresponding to this particle. So this thing already absorbs all of the little group transformation of this amplitude. And then what I have left is only a function of SU. Also, I'll remind you that there's some relationship as S plus T plus U equals to m squared, where m is the mass of these guys. So I can always remove one of them. And then even better, Bose symmetry, the fact that I can swap these two particles and the amplitude shouldn't change. So if I swap 1 and 4, actually this tells me that this function is to be symmetric. Okay, so what do we know about this amplitude? So now we just impose the little group, and we have some function here which we need to determine, but it's a function of these Lorentz invariant variables. So what else did we learn about amplitudes in general? Which properties should they have? So now we have a 4-point amplitude, not a 3-point amplitude. So what else do we have? So I can just think of the momenta as being complex, so causality is already kind of automatic. Now we are writing, let's focus on tree level. So tree level, we know that this function will be some rational function. So it can only have poles. So where can it have poles? Yeah, when some particle goes on shell. Okay, so this amplitude must contain poles. When S goes to m squared, right, I could have the amplitude factorized as such. I could have a scalar which propagates a long time, right? So I have that the amplitude, this 4-point amplitude should go like 1 over S minus m squared times the amplitude for 2 scalars and 1 graviton, right? So let me just write it. So if this is like 1, 2, 3, 4, and let me call this P, right? This will be something like 1 P being scalar, 2 being, I guess, helicity, -2 times A, and then I will have minus P, 4, and then 3. Okay, and similarly, when u goes to m squared, I will have the same thing, but flipping 1 and 4. So it has to have poles at s equals m squared, at u equals m squared, and finally also at t equals 0. So what does t equals 0 mean? It means that p2 plus p3 go to 0. So what does this look like? So it must look like a process like this. So I could have a graviton being exchanged, right? And then the amplitude will factorize as 1 over t times now the amplitude of 1, 4, and some graviton with momentum p. But now, because I could have either helicity going through to sum over all possibilities, so I will just have some helicity, and here I will have the opposite helicity because I choose an all-outgoing notation, 2, 3. Okay, but there's not so much freedom because I already put this factor here. So this factor has a very high dimension. Okay, so notice that each one of these brackets has dimensions of 1 derivative. So this whole thing has dimensions of 2 derivatives to the 4th. So this has dimension 8. So this function here has to have a high negative mass dimension. So the only answer that I can write that is able to have all of these poles will be of the following form. I will have this function of kind of s, u, and t, which will be minus s minus u so I can only have this form, s minus m squared, u minus m squared, t, plus some polynomial. The reason is if we try to separate these poles, then we already counted the mass dimensions of these guys. These were like 2 derivatives, right? But this thing here already has 8 derivatives because I have 4 momenta, and each pair of these is like another momenta. Okay, so just by dimension analysis, this is the only answer I can write. And now let's check this factorization to determine this coefficient here. Okay, so what is this product here? Let me just write these amplitudes. So the statement is, once again, that when s goes to m squared, then this should go to the following amplitude. 1, 2, 4. So let me write the amplitude on the left and the amplitude on the right. So we just wrote them before. So we had this kappa prime x squared. So what was x? X was this reference spinner, 1, 2, because now 2 is a graviton. 3 is a graviton, sorry, yes. This also has a kappa prime. Okay. So this is a scalar. So now okay, here I have negative helicity, so this needs to be angled. I have positive helicity, so this needs to be square. And now for simplicity, I can just choose the references. So the reference here to be the spinner on the other side, okay? Because these were completely arbitrary. So I can make now any choice that I like, because now I have enough momenta available. So this thing equals kappa prime squared, what, like 2, 1, 3, 2, 4, 3 squared divided by 2, 3 squared, 3, 2 squared. So let me rewrite this. So first of all, remember that product of square and angle was the same as the product of the momenta, right? So this thing, 2, 3, 2, 3, this is the same as 2 P2 dot P3, which is the same as T. Okay, so this thing is kappa prime over T squared. And then the other thing I'm going to do is I'm going to use momentum conservation, and I'm going to write 4 as 2 plus 1 plus 3. So this is P4 that appear here. Okay. But now there's this nice property that, remember, because 2, 2 equals, or 3, 3 equals 0, whenever we have a momentum, massless momentum, multiplying the corresponding spinner, this is exactly 0. Because this will be kind of 1, 1, lambda tilde, like I, lambda tilde I, and this is 0. Et cetera, et cetera. Okay, so actually I can throw away these 2. So this will be the same as minus 2, 1, 3. So this is simply 2, 1, 3 to the 4th. I remember that this was the prefactor that we had written. So I guess I just erased it. But I told you that the amplitude was 2, 1, 3 to the 4th times this function of S and U. Okay, so factorization checks out. That tells us that this needs to be, so here we just have the same prefactor. And what happens here, you can just check that when S goes to M squared, U minus M squared, because of this relation here, goes to T. Okay, so U minus M squared, when S equals M squared, is minus T. So indeed, if we just take the limit here, we will get a 1 over T squared. So this precisely reproduces this thing here. So we find out that this beta, let me write it there, is not a new parameter. It's just the square of the 3-point coupling with a minus sign. Okay, so it's fixed by unitarity. We can see that even though we made here some ansatz, then the coefficient is fully fixed by unitarity. And now, I won't have time, but I will leave it as an exercise to check the other channel. So what's the other channel? This one I wrote down here. Okay, so I gave you the expression for the 3 graviton amplitude and the expression for the 2 scalar 1 graviton. Right, so there's another factorization channel. So now the limit when T goes to 0 of this amplitude, 1, 2, 3, 4, now will be kind of the sum over helicities of this P, so this will be P, of this, the product of these amplitudes. So as an exercise, just use the expressions that we wrote for this 3 graviton amplitude, and the 2 scalar 1 graviton, and showed that this is minus 2, 1, 3. Once again, it had to be because of the little group divided by S minus M squared times kappa prime, which was the coupling of this, and then kappa. Okay, so that also tells us that beta has to be minus kappa prime. But before, we had learned that beta had to be, because I raised it, but it also had to be minus kappa prime squared, which means that even at 3 points, we really only had one 3-point coupling of gravitons to scalars and to gravitons themselves. So what is this? What is the name of this relationship? The fact that gravitons couple to anything with the same strength. Yeah, so this is the equivalence principle. You see that here I didn't have to impose general covariance, gauge symmetry, anything like that. I just imposed all of these basic principles, Poincare symmetry / Lorentz symmetry, these little group transformations, and then this locality and unitarity of the 4-point amplitude. And as a pure consistency check, I obtained that there's only one 3-point gravitational coupling, which is Newton's constant at this order in derivatives. Okay, and I reconstructed the factorizable part of this amplitude. Okay, and this polynomial, now it's trivial to write. So this polynomial is any SU symmetric polynomial. And what does this correspond to? This would just correspond to higher derivative terms. Right? So for instance, in this polynomial, now I can write, so this could be like a constant, call it G4, G6T, G7, SU, plus dot, dot, dot. So anything which is symmetric under the exchange of S and U, which also fixes T. And what is the interpretation of this? This is a new coupling. So this is just a coupling of phi r squared, phi squared r squared. So some new 4-point coupling. This one here will be phi squared derivative of Riemann squared, et cetera, et cetera. Okay, so we just find that, okay, this one here is a bit more complicated because it will have 4 derivatives, so this will be like, okay, so we don't need to write all of these Lagrangians with all of these expressions in terms of curvatures, which are very complicated in terms of the metric. If I just want to write the most general scattering amplitude of 2 scalars and 2 gravitons, I just need to impose all of these basic principles and write the most general expression, and this will be it. This will be exactly what you get when you compute from your Lagrangian, and we didn't need any extra input. We had, for instance, the equivalence principle appear as an output. And in fact, you can play the same game in Yang-Mills theory, so you can construct the 3-gluon amplitude. You will have some antisymmetric structure constant, and if you impose consistency of factorization of locality and unitarity, just like we did here for this graviton scattering amplitude, then you'll find that it's only satisfied if the Jacobi identity is satisfied by these structure constants. Okay, so we don't need to input any Lie algebra anywhere in our calculation. We just write the most general 3-point amplitude. We impose consistency of the 4-point amplitude, and as a pure output, I won't have time to do it, but you can try, and you will see that you will learn that secretly there's some Lie algebra which is controlling the dynamics of 3 massless spin 1 particles. Okay, so this goes to show what I try to. So hopefully I convince you a little bit that indeed these basic principles are extremely constraining and are very powerful as a calculational tool to compute this scattering amplitude. So we were essentially able to guess the formulas for these amplitudes at 3 level just using the basic principles without introducing all of this extra machinery of gauge symmetry, et cetera, et cetera. Do you have a question? Ah. Okay. Are there any questions? Yes. Can you say it louder, please? Okay.
Thanks. Okay, I understand your argument that you make a factorization, yes?
Yeah.
And my question is, the equivalence principle is a consequence of the unitarity of the amplitudes?
Yes, that's right.
Okay.
Yeah. So we impose that the coefficient, the residue of this pole in the T channel is given by the product of 3-point graviton amplitude and 2 scalar 1 graviton amplitude. And in the S channel, which I raised already, we imposed that it was the product of two scalar 1 graviton amplitudes. And that is only consistent if the couplings that govern both of those 3-point amplitudes are exactly identical. Right? Because in one case, we got that the coefficient of this thing here had to be kappa prime squared. And the other one, we got kappa kappa prime.
Yeah, but we consider scalar particles, but
Yes.
it's possible to generalize?
Yes, you can check that the same exact thing will happen if you just have this particle to have arbitrary spin.
Okay.
So here I did the simplest example, but exactly the same thing will happen when particles have a arbitrary spin. And also something else you can learn, for instance, you see we had these equations that fix the 3-point amplitudes, and nothing stopped me from solving those equations for helicity greater than 2.
Okay.
Right? So in principle, I could have considered massless higher spin particles, and then something would go wrong when I try to impose this factorization check. So the 3-point amplitudes are perfectly well defined, but we know that there is no theory of interacting massless spin 3 particle in flat space, and indeed you will see that what we will go wrong is that you won't be able to impose factorization consistently in all channels. When you impose factorization in one channel, you get some very high order pole. So here, there was this crucial fact that we had this S minus M squared that became just T. So in the limit, we just had a 1 over T squared, right? If you did the same for a massless higher spin, you will get a very high order pole. And that wouldn't be consistent with the local theory.
Okay,
So
thank you.
you can also learn that there is no theories of interacting massless higher spin particles, like essentially Coleman-Mandula, just from these basic principles. Yeah.
Yeah.
Yes.
If I have some non-abelian gauge theory, do I need to say something else to impose something else on the amplitude or something?
No, it's exactly the same thing. You will impose factorization, so consistent of locality unitarity, now with gluons, and then you will find that indeed it's only consistent if the coefficients. So now, let me just write it quickly. So the amplitude for 3 gluons. So for instance, let me write the amplitude for 3 gluons. So -1, -1, +1. So this will be 1, 2 cubed, 2, 3, 3, 1. But then you can check, for instance, that this thing actually is not both symmetric under the exchange of 1 and 2, because here I have a cube. So if I exchange 1 and 2, this is invariant, but this picks up a minus sign. Okay, so the only way to make this both symmetric is that I actually have like an F1, 2, 3 constant here, which is antisymmetric in the 3 indices. Okay? And then what you will find is that now you will have to keep track of these extra indices. So I cannot have a single spin 1. I need some like 3 indices that tells me that I have several species. First of all, that's the only way to satisfy both symmetry and little group invariance. So you already learned that there's an antisymmetric structure constant. And then when you play the same game of compatibility between S, T, and U channel, you will learn that it's only compatible if these things satisfy the Jacobi identity.
Okay, thank you.
Hi. Well, you solved this problem like for 4 particles, but for like 10 or when does this all machinery stops?
It doesn't. So you can actually do this systematically at high orders, and it always works, and always the ambiguity, the only things that you cannot fix are always new couplings that you could have in your theory. And indeed, there's even a systematic way to do this. So here we were playing this game of imposing consistency in one channel and the other, but there's a systematic way, so one can build a recursion relation using this idea of factorization. So I don't have time to describe, but there's something called the BCFW recursion relation, which essentially you do some complex deformation of the amplitude, and you use Cauchy's theorem, so you know essentially where all the poles of the amplitude are, consistent with locality, you know all of the residues, so essentially you can do some contour deformation argument that allows you to write a recursion relation that writes higher point amplitudes in terms of lower point amplitudes. So indeed, this always works. We can always construct more complicated amplitudes from simpler amplitudes. Okay, here I was focusing at tree level, but it turns out that the integrand of a loop amplitude is also a rational function that satisfies all of these properties. The things that gives rise to these logs that I mentioned yesterday, inside of the integrand is still a bunch of poles. So there's a general tool called the unitarity method that one can use to systematically construct integrands, also imposing unitarity, locality, et cetera, so we can do any loop calculation also, always without ghosts. So because see here at every stage I had gauge invariant amplitudes as building blocks and physical states, actual on-shell particles crossing the various kind of on-shell legs. So so it's a fully general set of ideas that at least in perturbation theory it always lets us compute anything.
Thank you.
So I have two questions. The first one is, in flat space, we know that the asymptotic states are ill-defined because we have IR divergences.
Yes.
What happens with that here in this formalism?
So the IR divergences come after integration. So if you apply these ideas at the integrand level, there is no issue. So you just reconstruct the full integrand for the loop amplitude, just from knowing that where the poles are. Because okay, here at the end of the day, this idea of locality is just that we know that amplitudes are built out of propagators, and that when I put it on shell, then I have everything that can go in between. And that's true also for an integrand of a loop amplitude. Before we do the loop integral, we also have a bunch of propagators, so the same ideas apply. Of course, when you integrate, you will get an infrared divergence, but it's not an obstruction to just implementing this.
Okay, and then say that you have a theory which is UV finite.
Mm-hmm.
How will you see that the theory is UV finite or complete in this formalism? And can you use this to build new theories that are UV finite?
So notice that most of these constraints that we're applying are kind of infrared constraints. It's something that happens at low momenta when momentum goes to zero or hits the mass of some particle in the low energy theory, right? So here, I mean, if the theory is UV finite, once you do the loop integral, you will see that that it is indeed finite, and but this works generically for effective field theory. So see, notice that here I wrote, well, first of all, I'm doing gravity, which is not renormalizable, right? But I can just construct the most general answer. But after that, I have to kind of carry the usual program of once I do the integrals, I will have divergence. I will have to absorb them in these counter terms. But here I just wrote the answer. Instead of writing some Lagrangian and I add counter terms to the Lagrangian, I just wrote the answer. I can write the loop integrand also. I do the integral. If it has a divergence, I renormalize it, and the rest is history. Yeah.
Okay. I have a question. You said that for massless higher spin interaction, something goes wrong.
Yeah.
It's the same true for massive higher spin particle
for massive
interaction?
higher spin. Well, for massive higher spin, what goes wrong is the high energy limit. So you can, for instance, understand the Higgs mechanism by trying to impose that kind of high energy scattering of longitudinal massive spin 1 particles it doesn't explode. Yeah, but that's the only thing that goes wrong. All of this factorization can be satisfied in a consistent way, et cetera, et cetera. Yeah. Mm. It gets trickier when spin is greater than 2. So it just gets technically more complicated. But
okay. And the other question is, at what point do you assume that you are using just tree-level computation and there are not quantum corrections?
When I assume that the amplitude is rational. Yes. So here I'm just writing polynomials and poles. Right? Of course, if you have a loop amplitude, there will be logarithms. But there's a shortcut, which I mentioned, is that you can always think about the loop integrand and apply the same reasoning and reconstruct the integrand from unitarity and locality, etc.
For instance, in electrodynamics, that works nicely. Can you consider quantum correction in this formalism?
Yes, yes, yes. In fact, I mean, a lot of, I would say, half of the community that makes precision computations for colliders with like any kind of standard model process, they do it using these ideas. Yeah. Here I focus on gravity because the second half of the course will be about how to extract classical dynamics from this. But this is just to convince you that I can easily write gravitational amplitudes without having to do a lot of work with the ICTP-SAIFR action. Yeah. And then we'll use them for something.
Hi, I have a quick question. Do you know if these polynomials always factorize nicely or sometimes they don't? And how can you assure that they factorize nicely to find the poles?
So these are polynomials. So they don't have poles, which means that they're unconstrained by locality and unitarity.
And on the other side?
This?
Yes. Do you know that they always factorize in that way? Or?
So in this case, we achieved kind of satisfying factorization in all the channels. And so we claimed victory. But for instance, I mentioned this example of if instead of gravitons, I had massless spin 3 particles, then something will go bad. And I mean, you can see, I guess I just erased it, but you can see that we had this 1 over t squared that came from the denominator of this x squared. So my 3-point amplitude was kappa prime x squared. If I have a massless spin 3, it would just be x cubed. But then I would have a 1 over t cubed. But 1 over t cubed I cannot recover with just poles in 3 different channels. So you will see that in that case I would fail to satisfy factorization in all the 3 channels, or I would see a breakdown of locality.
And what do you do then?
What do you do? Well, that just tells you that it's a bad theory.
Okay.
That theory is not a consistent interacting theory.
Okay.
Yeah.
Thank you.
Just a small one for clarity of the exercise. When you wrote the 3 graviton amplitude, you had the 3 particles on shell.
Yeah.
Here, this one doesn't need to be, right?
Well, the particles outside are on
outside,
shell.
yeah. But using the 3 graviton expression.
They
we
are
had
on
before.
shell because of this limit.
Okay.
So when I take t to 0,
Even the.
yeah, because I'm taking p1 plus p2,
You take this one, right?
which is the momentum of this leg here.
Yeah.
So because I'm taking t to 0, which is this momentum squared to 0, I'm putting this leg precisely
Then
on
you
shell.
can use.
And that's why I can relate it to the 3-point on shell amplitudes.
Right.
Yeah.
Thanks.
Okay.
So,
Okay. If there are no more questions, we go to the coffee shop, to the coffee break. You can also go to the coffee shop if you want. We reconvene here in 20 minutes. Yes, 20 minutes, please. Thanks.